All right, class, sorry about the delay due to open house and just life. Okay, so we're going into chapter 4. We're going to do 4.1 through 4.3 here. All right, so 4.1, we're getting to solutions and solution chemistry. And this is an area where you have limited exposure. So we're starting to get into kind of unknown territory at least, or probably weaker understanding. So solutions are just easily defined as mixtures of two or more pure substances. So typically you're using water and some other something dissolved in there to make a solution. And the solvent is present in the greatest abundance, and the solute would be all the other things that are not in the greatest abundance. So most of the time the solvent is H2O, and then all the other substances dissolved in there are not. The only other times that I can think of, so like when we did the chromatography lab, the solvent that we utilized for that one was the isopropanol. So you can have some other solutions using something other than H2O. Okay, so when we talk about making a solution, we need to talk about like when something dissolves. Okay, so the idea of dissociation. Dissociation is when an ionic compound goes into solution. So rather than it like being Na and Cl stuck together, when an ionic compound goes into solution, it separates completely. So the ions actually are now apart from one another. So in the image there, you can see you got your solid NaCl there. And then as the water dissolves the salt or dissociates the salt, basically the ions, the individual ions are separating out, attracted to different parts of the water molecule, whether the positive or the negative. And this process is called dissociation. So that's ionic compounds. And things that dissociate, so ionic compounds that dissociate, create what are called electrolytes. And electrolytes are ones where you have ions dissolved in water. So you have ions present, and you can think of an electrolyte. So if it's not an electrolyte, it can't electrocute you. But if it is an electrolyte with ions present, then it could electrocute you. And a non-electrolyte, it may dissolve in water, but it's not going to dissociate. You're not going to get ions present. So the example here, what is that? That's CH4O. So that's methanol there. So methanol dissolved in water. Methanol does not dissociate. You don't get ions present. So if you were to like run an electric current through that solution, there would be nothing would be electrocuted. It would all just kind of run like normal. And so that's often the myth. Like often people think, oh, if I drop a toaster, why would you have a toaster? Let's say a blow dryer. If I drop a blow dryer in the bathtub, right? You shouldn't do that. Then you're going to electrocute yourself. Well, not always true, because technically pure water does not conduct electricity. But the minute a person slides into a bathtub, all the salt that's on their body from sweat, that dissolves into solution, and then you create an electrolyte that is the solution, and then you can electrocute yourself. Not that you guys have enough hair to blow dry anything. Anyway, okay, so electrolytes, non-electrolytes, weak versus strong. Okay, so ionic compounds, all ionic compounds are strong electrolytes because they dissociate. You get positive and negative ions. They're gonna be electrolytes. And then when it comes to molecular compounds, you've got a variety. So strong electrolytes, if it's a strong acid, it's going to be an electrolyte because you're going to get all these H pluses and then negative charges as well. And then for weak acids and weak bases, those are also going to be good electrolytes. And then anything else that's molecular that isn't an acid or a base is not going to be an electrolyte. It's not going to do anything. It's not going to conduct electricity. All right, and I kind of went through all this concept. Molecular compounds tend to be non-electrolytes like for acids and bases. Got it. All right, moving on. Okay, so, and this is kind of the definition of, or kind of a picture talking about like an electrolyte. So, and remind me on Friday, but I will we'll pull out like the little light bulbs and we'll test it again. So a strong electrolyte dissociates completely when dissolved in water. Great. Weak electrolytes only dissociate partially when dissolved in water. So weak acids and weak bases, only some of it dissociates. So like a weak acid, some of them are going to donate hydrogens, but some are going to stay as a compound. So an example of a weak acid would be vinegar. So vinegar or acetic acid is a weak acid. So it's also a weak electrolyte. So some of the acetic acid donates hydrogens, but others do not. So it's kind of this mix. All right, so let's look at our examples of strong acids. You kind of reviewed these during the summer, but so strong acids, so strong electrolytes are strong acids, strong bases, and soluble ionic salts. Okay, so all of those, and this is where those solubility rules come into play. So if it's a compound that always combines with, if it's like a metal that's combined with a nitrate, then it's always going to be soluble. No exceptions. Okay, same thing for the acetate ion. But then there's some exceptions when you get to like some of the halogens and sulfate. And so we're going to try to apply these because there's something it's going to come up, and we'll just have to utilize the skill to kind of determine, oh, is it soluble? Is it insoluble? And how does that apply to electrolytes? All right, next type of, so when we talk about solutions, a very common form of reaction, when we have two solutions, we combine them, we get a precipitate or a precipitation reaction when a solid forms. So the example in this picture, this is probably potassium iodide combining with lead nitrate. And then you get lead iodide, which is that yellow cloud that's forming. And anytime like two clear solutions come together and you get something cloudy, that cloudiness, that is a precipitate. That's a solid. Although it looks very, it doesn't look like a solid. It's just kind of floating in the water. It is solid because it's no longer dissolved in solution. You can see it. It's eventually going to settle to the bottom. So all examples of something that's insoluble. And then you can use the solubility guidelines that was on the previous slide to predict what type of product is going to form if you know different things that are coming together. And you will definitely do this at some point as we go along in this course. All right, so so an exchange reaction, and another way that I think it was exchange reaction in your textbook, but they're also called like, in this case, it's going to be a double replacement reaction. And it's in this textbook, it's called a metathesis. Comes from the Greek word that means to transpose. Very fancy, very fancy. But so if you look at it this way, you've got two different solutions. They come together. You're going to get a solid form. So that's going to be your precipitate, the silver chloride, and then you have this potassium nitrate that's just floating around. They're just ions. They aren't together. Keep that in mind because these are ionic compounds coming together. All right, so when we pay attention to a reaction, it's really important to pay attention to what does the species, what form is it in? Does it start out as a solid? Does it end as a solid? Does it start as a aqueous solution? Does it start as a liquid? How does it change? And that allows you to predict what's the product or what are you going to see. So predicting what the reaction looks like. And we did this a bit in first year chemistry as well. So if we understand reactivity, we must be aware of just what is changing during the course of a reaction. Like, how is this reaction changing? And that's often, so if a reaction is written with the states present in that reaction, there might be a reason for them putting that in the formula so that you can do some predictive processes. All right, next, the molecular equation lists the reactants and products in their molecular form. Kind of talked about this already. Okay, so, but then we have what is called an ionic equation. An ionic equation is when you take, so if it's aqueous, you're going to take the different entities and you're going to split them apart, because if they're aqueous, then they're ions are floating around, they aren't like actually linked together. So you don't actually have silver nitrate solution. You have silver ions and nitrate ions floating in a solution. So it's just a big kind of mixed bag. And then what you do, so you kind of break everything apart, and then you remove the species, because technically this is really what's going on in the reaction, rather than the previously written one. And when we do a net ionic equation, we actually cancel out the ions that don't change from beginning to end. So in this reaction, the nitrate and the potassium are ions both in the beginning and in the end, and so we cancel them out and we simplify the reaction to just show the ions that are reacting with each other and forming the solid. So it's not the full picture of the reaction, but it simplifies it down to really what is interacting and doing stuff in that reaction. All right, so those ones that we canceled out, those ions that we canceled out, we call those spectator ions, because really from the beginning to the end of the reaction, even though they're present in the beaker or in the reaction vial, they aren't doing anything. They're just kind of floating around, doing nothing. We call them spectator ions for that. All right, so when you want to write a net ionic equation, first of all, you write a balanced molecular equation, and then you break apart all the strong electrolytes, like split them up so that you have all those ions written out, and then you cross out anything that remains unchanged from the left to the right. So kind of what I was describing earlier. And then you write the net ionic equation, or the simplified version, once those spectator ions are canceled out. All right. This is kind of our last section, is on acids and bases. So we looked into acids a little bit last year when we were doing toxins, but Arrhenius acids are defined as things that cause the concentration of H plus to increase. And Bronsted-Lowry acids are define them as proton donors. So they donate protons typically to water. And there are only 7 strong acids that exist. So HCl, HBr, HI, and then nitric acid, sulfuric acid, chloric acid, and perchloric acid. Okay, so those are the only ones that are strong acids. So if you ever see those ones are going to completely dissociate. So when you think of like net ionic equations, you're going to separate those out. All right, bases, on the other hand, Arrhenius defined bases as substances that increase the concentration of OH minus. So we get more OH minus dissolved in solution. Bronsted-Lowry are defined as proton acceptors. So they accept extra protons, or in the case of if there's an acid present, then the base would accept the proton from an acid. So the strong bases that exist are ones that are metal salts made with hydroxide. So all the alkali metals combining with hydroxide ion are strong bases, along with calcium, strontium, and barium hydroxide. So then when you think of an acid-base reaction, in an acid-base reaction, the acid donates a proton to the base. Okay, so the water in this case is going to be would be defined as the acid, because it's donating a hydrogen to the ammonia, and the ammonia would be defined as the base because it accepts the proton. So when you talk about a neutralization reaction, like you want to cancel out the acid with a base or cancel the base with an acid, you're always going to have a salt, or typically you're going to have a salt as the product as well as water, because in the neutralization the OH and the H combine to make H2O. So when a strong acid reacts with a strong base, the net ionic equation is always producing water, right? It's H plus OH minus produces water, because the spectator ions, the NAs, the Cl minuses, they're just kind of there, but they aren't doing anything. So a neutralization reaction, if we're to simplify a strong acid with a strong base, it's really just the production of water, bringing those ions together. All right, so gas-forming reactions, ones where we get bubbles coming off, So some metathesis reactions do not give the product expected. So in this reaction, the expected product, H2CO3, decomposes to give a gaseous product. So we have hydrochloric acid combining with calcium carbonate. Okay, so the predicted product would be H2CO3, but that doesn't last, like it just decomposes immediately the minute it forms, and so then you end up having CO2 coming off, and then uh, you have the calcium chloride left behind. So a slightly different product versus what you would expect with the HCl and a compound. So when a carbonate or a bicarbonate reacts with an acid, the products are a salt, carbon dioxide, and water. So slightly different product. And this will come into play, especially in the AP exam when you have to predict the products of a reaction, where they really give you just starting material. They may not even give you the formulas. They tell you how this thing and this thing just in words, and you have to write the whole reaction formula and predict the products. So kind of having that awareness of how carbonates react to acids will allow you to predict those products later on. And similarly, when you have a sulfite reacting with an acid, so that's SO3, not SO4, the products are a salt, sulfur dioxide, and water. So rather than the sulfur or the carbon dioxide with carbonates, this is a sulfur dioxide and water. So very similar in that sense. So this reaction gives the predicted product, but you had better carry it out in the hood, or you would be very unpopular. So that's really smelly, kind of sulfur, terrible, kind of like a stink bomb kind of smell. And we're not going to do it in class. Thanks for asking, though. All right, so that's it, and I will see you on Friday.